The method of sections for analysis of simple trusses. Our objective is to analyze the forces in truss members using the method of sections and discuss other application of this method. As such, we are going to have a reading quiz. We're going to discuss some applications. We are going to go over method of sections. There's a concept quiz. There's a group problem that we will solve, and there's an attention quiz before we can wrap the session up. Reading quiz. In the method of sections, generally a cut passes through no more than blank members in which the forces are unknown. The answers are A1, B2, C3, and D4. The correct answer is C3. And the reason for that is we have three equations of equilibrium available to us. Having three unknowns, three equations of equilibrium, we should be able to solve for the three unknowns. Reading quiz 2. If a simple truss member carries a tensile force of T along its length, then the internal force in the member is blank, A, B, C, and D. You can read through all the answers, and there are tensile forces and they're compressive, and both are given. First, we need to determine that if we can just look at the answers and come up with the answer. Let me go back to the problem. If a simple truss member carrying a tensile force of T along its length, the internal force in the member is, again, the force is tensile. It is carried by the member along its length. Then we try to determine what the internal forces would be. That means that the tensile forces in the member is of magnitude T. So really the D is the correct answer in this case. So D would be the answer. The reason for that is if the member carries a tensile force of T along its length, we mean by that there will be tensile forces in the member of magnitude T. That's how we can interpret when a member carries a tensile force of T along its length. And that's how we interpret the answer. Some of the application of trusses in general and the method of sections in particular. As you know, we can have many large trusses. Two of them are shown here. One is a large mobile crane, and that's shown here on this figure on the left-hand side right here. And the other one is the huge power plant. It's actually transmission lines that would be carried by this huge transmission towers. So that's also another application of large trusses. So if we would like to know the forces in a specific member of any segment of any of these trusses without going through tedious joint by joint calculations, we can use the method of sections. It is pretty straightforward, and it is a very efficient method for determining the forces that needs to be determined in specific members. So what is involved in the method of sections? We divide the truss usually in two or more parts depending where the cut can go through. In this case, since there is one simple truss and the cut would divide the trust into two parts. So cut AA, that's shown here, and that goes across member BC, member CG, and member GF would be our chosen cut for this specific trust. Most likely the reason for that is we would like to find the forces in member BC, CG, and GF, or any of them, BC or GC or GF. So first we make a cut through the entire portion of the trust, or only through some sections of the trust. Since we know that the trust members are subjected to only tensile or compressive forces along their length, as such, we would determine the internal forces at the members that have been cut. We will also, these forces would also be either tensile or compressive, and not both of them combined, although there might be members in which there could be a tension compression type of members in a truss, but those are unusual, and we don't look at those type of cases here. So a member is either in tension or in compression. If the member is in tension, as such here on this particular figure that I just checked, then the forces are shown as such. And it's important to understand this type of an analysis, because after we make the cut, you would see that we show the forces by two arrows applied at the end of the member. One is at the end of the member itself, the other one is at the end of the cut. Whereas if it is compression forces that I just showed by a check mark, the situation is reversed. You can have a member in compression, meaning that the forces are pushing on the joints at two ends, and when we make the cut, the internal forces are shown as such. So it's important to realize that. Then after we identify the members, we identify the forces, then we would use the principles of equilibrium and Newton's third law to determine the forces within each member. An example that we just saw previously, the cut is made through members BC, CG, and member GF, the way it's shown. If we would like to determine the unknowns, in this case, the forces in member BC shown by F sub BC, force in member GC shown by F sub GC, and force in member GF shown by F sub GF. In that case, we need to come up with our equilibrium equations to be able to solve that problem. If we look at the left hand side of the problem, left portion here, this is the left portion of the cut, or the portion to the left of the cut, and this is the portion to the right of the cut. As you can see, it seems that this right hand side, this one is more complicated. So right off the bat, our intuition tells us that we should look at this section first to see if we can calculate the unknowns. Then if we cannot do that, then we are going to move the other section to the right. So we determined that based on two things. Number one, where is it that we need to determine the forces? What are the unknowns? And number two, what are the total number of unknowns after we make the cut? We want to make sure that the number of unknowns does not exceed 3 in general. Then we decide which side of the cut is easier to work with. as I just discussed. Then we would determine any necessary support reactions by drawing the free body diagram of the entire truss and applying the equations of equilibrium if that also needs to be done. Part 4, we draw the free body diagram of the selected part of the cut truss, and we would take a look at all the internal forces and that are present at the location of the cut. We also would take a look at the external forces that are also applied to the entire section. It's very important to note that the external forces must be included when we look at that particular section. In this case, there's 1,000 Newton external forces that are applied to the cut that we made, the left hand side of the cut as shown here. So as with before, we assume the forces to be pushing away or pulling away from the joints. We assume those are in tension, and if it turns out that the answer is negative, then that means the original assumption needs to be switched. But we don't do that until the end. So if the answer is negative, it's important to keep that negative answer and carry it on through our calculations. Then we would apply the scalar equations of equilibrium, E of E. We summarize that. We've been using that symbol throughout, E of E, equations of equilibrium, to the selected cut section of the truss to solve for the unknown forces. Remember that in most cases it is possible to write one equation to solve for one unknown directly. So we want to make sure that we look for that and take advantage of such a shortcut rather than making life difficult for ourselves and look for the longer method. So we look for any possible shortcut that we may actually find for the solution. Let's take a look at an example. In this case, truss A, L, K, J, I, H, G, F, E, D, C, B is actually shown. And I actually read this to you clockwise. You can also call that any other way that you like, as long as you stay consistent either clockwise or counterclockwise. Loads are shown on this truss. We would like to determine the forces in members K, J, K, D, and CD. Let's look at the members first. The members are KG. Remember, we don't know the location of the cut yet. So we would like to determine the forces in member KJ, member KD, and member CD. We may not even know if we should use method of sections or method of joints that I covered previously. So in such a case, first we need to determine what method to use. It makes sense here, since we are looking for forces in 3 of the members only. It makes sense to try to solve the forces by using method of by cutting a method of section, by making a cut through a section and actually look at that. So we're going to use that. Now, how do we determine the location of the cut? In this case, again, we look at the unknowns. We would like to determine the forces in members KJ, KD, and CD. As such, we would make the one cut and try to solve the problem. If that one cut could be made through and it can go through those 3 members, that'd be fine. Now, what if on top of KJ, KD, and CD, I would like to find another member, another force in a member, for example, IH. In that case, of course, more than one cut needs to be made. Now, what if, for example, only member EF is of importance? Or what if there's only two members? For example, if it is EF and FH, can I just cut these two members? In that case, it seems to be much easier to look at, for example, joint F. Is it possible? How many possible ways can I make a cut through a member? Well, remember that depending on which member we are looking at, there are different ways that we can do this cut. And of course, for this, we can also make the cut any other way, but we chose the shortest cut, which is a straight line that can go through all the unknowns that we would like to calculate. It is possible that the truss could be much more complicated than this, and the location of the cut may not be as easy as we saw here to determine. But it's important to make a determination as to what is the best section, best cut that can go through the section, so makes our life a whole lot easier to calculate for the unknown. So the plan is to take a cut through the member KJ, KD, and CD, work with the left part of the cut section. The reason for that is because there are in this case less members to the left. It's shorter, it seems easier, and we determine the support reactions at A, and the reason for that is because we don't know the support reaction at A, and in order to solve such a problem, we need to determine that, and then we would apply the equations of equilibrium to find the forces in the unknown members. So first, we are going to use the entire the free body diagram of the entire section to calculate the reaction at support A. And it's important to realize how we can do that. We take the free body diagram of the entire truss. We show the reaction of the supports, and we would solve for the three reactions, which could be treated as three unknowns in this case. Remember, for such a truss, such a truss, we are going to have two reactions. One is in this way, one is in this way, and for G there will be one reaction perpendicular to this surface that I just marked by red. So there will be three of them, and there will be three unknowns. We take the summation of forces in the y, set that to 0. The summation of forces in the y direction, which is upward to the page, we call this y, and we call this x. Okay. In the y direction, the summation of forces would be 30 plus 20 plus 40, or 40 plus 30 plus 20, that's 90. And so that's one equation. And then there will be taking a moment about one of the supports and calculate the other, calculate all the moment that are caused by the external forces, and that, calculating the reaction. So in that case, we take the summation of moment about G, knowing all the moment arms, we would have one unknown, which would be the reaction, the vertical reaction, or the reaction in the y direction at support A, and we would calculate that as such. So let's, after doing the calculation for the reaction of the support at A, and that turned out to be 45.6 kilonewton, okay, as it is shown down here, and I just explained that to you. A sub y would be 45.6 kilonewton for this problem. Then we would take the moment about a point D. In this case, you would like to calculate the forces F sub kj, and this makes our calculations a whole lot easier. Taking a moment about point D. Remember, for this section to be in equilibrium and remain in equilibrium, the summation of moment about any point, even outside the cut, must be 0. So that's how the principles of statics, equations of equilibrium that we use. So summation of a moment about point D, we set that to 0. What are the forces that are causing the moment about point D? It is F sub kg, that's one of them. This is an unknown force that causes that. What about F sub kd? Do we need to worry about that force and x and y components? Not really, because the force goes through the point that we are trying to take the moment about, and that would be 0. Also F sub cd, we don't need to worry about that because that also goes through the point D. So none of them would cause any moment about point D. And there are 3 other forces that are known. They are also source of moments about point D. One is the reaction, 45.6. The moment arm would be 9. So we simply multiply 45.6 times 9. Again, this is causing the clockwise moment, but according to our sign convention, we assume counterclockwise to be positive. Also, the 20 kilonewton and 30 kilonewton, they're acting downward. They're causing the counterclockwise moment, which would turn out to be positive. So we take into consideration the moment arms of 6, and for this other case of 30 kilonewton, the moment arm would be 3, and this is the unknown F sub kj multiplied by 4. That's the moment arm 4 meter. F sub kj is unknown, is causing a clockwise moment about point D, so it is shown by a negative number. We have one equation, one unknown. We can easily solve for F sub kg. If we solve that, it's going to be minus 50.1 kilonewton. It's actually in compression because the original assumption we made was we assumed member kg is in tension, and after we went through our calculations, we got a negative number as the force in a member. That would give us the indication that the original direction of the arrow wasn't correct, and it is actually in a compression. Note that I don't change the that yet, okay? So I keep that F sub kj the way the direction of the arrow the way it was pointing to the right. However, I'm going to carry the negative sign with me through the calculation. Then we're going to take the summation of forces in the y. We set that to 0. 45.6 is the reaction. Minus 20, minus 30, minus 4/5 of F sub kd, because F sub kd is can be it has 2 components. One is F sub dx and F sub dy. This is F sub F sub kd y. I pretty much provide a solid half of triangle, actually a triangle, as you can see. So F sub kd, that would be the x, the y component of F sub kd, which is nothing but 4/5 of kd. Again, we have only one unknown, that's F sub kd, and it's calculated as a negative number, and that means that member is also in compression. Note again that I don't change the signs here. I just indicate tension or compression, since the it turned out to be a negative number, and that means it's in compression. So knowing F sub kg and F sub kd is going to make it a whole lot easier to calculate our last unknown, which is F sub cd, by simply taking the summation of forces in the x direction. And remember, this is the x direction and this is the y direction. This is the customary x and y Cartesian coordinate system that I've been using throughout our course. As such, F sub cd would be calculated as a positive number, 53.4 kilonewton, and that means the member is in tension, since the original assumption of tension pointing away from the joint is correct. So that's really how we solve such a problem. Let's take a look at a concept quiz to see how you've been doing so far. Can you determine the force in member ED by making the cut at section AA? Explain your answer. And there are four options here. A, no, there are four unknowns. B, yes, using the summation of moment about D. C, yes, using the summation of moment about E, and set that to 0. And D, yes, using summation of moment about point B, and we set that to 0. So we are looking for member force in member ED. And let's see if we can locate that member first. That is member ED. I just shown, mark that by a red line. Member ED. How many can we make one section at AA as shown here? This is AA. Okay. We made a cut like that. We could also make a straight cut. AA could be just a straight line going through the member ED, EB, FB, and AB. And then if we do that and we take the summation of moment about point D or E or B, let's see if we can calculate the force in member ED. Can we do that? Let's think about it for a minute before I can tell you the answer. The answer is B. Yes, we can, using summation of moment about B, set that to 0. So let's see if we can take the summation of moment about point D. If we do that, and the only member that really causes any moment, it would be the ED, the F sub ED. And then we can find the shortest distance perpendicular to member ED, or we can take a look at the two components and find its relations with respect to that. Again, in this case, this component would go through B, so there will be only an X component of ED. So F sub X of E D would be of interest. We can pretty much solve for that one, knowing other forces that are also causing the moment, and those are mostly external forces. 1,000, 2,000, 4,000 here, 1,000 here, and 3,000, and this one doesn't come into play because it also goes through the point B. So we can actually do that. Let's take a look at another concept quiz, concept quiz number 2. If you know F sub ED, which one is F sub ED? ED is again the same member. I'm going to mark that by red. So if we know F sub ED, how can we determine F sub EB? Yeah, this is this other member. I'm going to put a double line over it to show what we're after. F sub EB B by taking section BB and using summation of moment about E, setting that to 0, by taking section BB and using summation of forces in the X is 0 and summation of forces in Y, we set that to 0 and calculate that by taking section AA and using summation of moment about point B, we set that to 0. By taking section AA and using summation of moment about point D, we set that to 0. The correct answer here is actually B. By taking section BB, using the summation of forces in the X, we set that to 0, and summation of forces in the Y, set that to 0. But try it and see if you can actually do that. Let's take a look at another group problem to solve. We call those group problem solving, since it's very important for all of you to go over that with me. In this case, given the internal drag thrust for the wing of an airplane is subjected to the forces shown. So this portion of a wing of an airplane, it has an internal thrust, as you can see. Of course, it's covered by the other material, but as you can see, the internal wing of this airplane, it consists of a truss, and what we try to do is we try to calculate the forces in member IH, BH, and BC. So member IH, member BH, and member BC. These are the members that we would like to calculate the forces in. So the internal forces were those members. We would calculate those, then we can size the members. But first we need to calculate those if we ever want to design such a truss for the wing of an airplane. Obviously we need to know about the forces first before we can proceed with the design. So we would take a cut through these members. Cut could be really any type of a cut, and it is going to look something like that. And then we would analyze the right section, not the support reactions, because that would save us calculating the reaction of the supports. Then we don't need to worry about those. And then we would draw the free body diagram of the right section. We apply the EFE, equilibrium of equations of equilibrium, and then we would try to solve for the unknowns. You can also try other methods to see if you can get the same result. So the right hand side of the cut that are made here, shown by a pink purplish type of a cut, is shown here. I actually I went over that. We look at the right hand side, we can simply take the summation of moments about point H, we set that to 0, and we can analyze the truss. We could also take the summation of moment about point B and calculate F sub IH first, and from there we could have carried on the calculation. So that is also a possibility. First here, in this case, we took the summation of forces in the Y direction. We set that to 0. This is our Y actually to the top of the page, and this is our X to the right of the page. This is our way of showing Cartesian coordinate system for our calculations throughout our lecture. So F sub Y would be 80 plus 60 plus 40, and there'd be one component acting downward, and that is the X component of F sub BH. And we consider that by taking the sine of 45-degree angles. Remember, this is a 2 and 2. The sides are 2 feet each, and so this is going to be 45 degrees. And so we take the sine of that, set that to 0, and then it turned out to be that F sub BE is 255 pounds in tension. F sub BE, right? Right? Let me go back to the problem here after finding the forces in member IH, BH, and BC. as such, this is going to be actually F sub BH. Okay, there's a typo here. This is not really E, but it's actually F sub B sub H. And let me correct that while we are going over this problem here. That would be B H, not B E. We don't have that at all. So that's okay. All right, good. There we go. It's actually got corrected. So it's actually F sub B H, 255 pounds. This is the F sub BH. That is the this actually was the Y component of F sub BH, but this is F sub B at 255 pound. And the reason for that is, again, it's in tension because we assume it was away from the joint, and it turned out that the answer is positive, so it is actually in tension. Then we take the summation of moment about point H and set that to 0. As such, we are going to calculate F sub BC as 130 pounds, and then we take the summation of forces about in the x direction. We set that to 0. We set that to 0, then that means F sub IH minus 130 and minus 255 cosine of 45 degrees. And that would be the summation of forces in the x when we set that to 0 for that particular cut. So we are setting the summation of forces, set that to 0 for this particular cut. So F sub BC turned out to be 130, so we're going to make sure we consider that. F sub IH is the unknown acting to the right of the page by our assumption. F sub IH is the unknown, and there would be one more component, and that is the this component, F sub BH, Y, F sub Y BH, and that would be 255 cosine 45 degrees. Set that to 0. We calculate that F sub IH at 310 pounds, and that's also in tension. Let's take a look at an attention quiz before we wrap the session up. So there are two attention quizzes here. Number 1, as shown, a cut is made through members GH, BG, and BC. So this member, and this member, right? Which section will you choose for your analysis? Let me see if I can move this a little bit. There we go. Okay. So we go back. There you go. So we made a cut through these members, and I would like to determine the forces in them. Which section will you choose for analysis, and why? Right, because of the fewer calculations. Left, because of the fewer calculations. Either right or left, same amount of work. None of the above. And the answer is we are going to pick right because of the fewer calculations. In that case, we don't need to worry about calculating the reactions at I and A. So that's the correct answer because of the fewer calculations. And the second one is we are trying to we're determining the force in member HG. This is member HG in the previous problem, the same problem that we just looked at. Which one equation of equilibrium is best to use? And you can examine this. In that case, we would like to take the moment about a point that would have more forces going through it, because for the forces that are going through a point, they're not going to cause any moment about that particular point. In that case, point B seems to be the best because both forces in member GH, member GB and member BC is going to go through that. So And that's the best way to do it, actually. Take the moment about the point A and set that to 0. So the correct answer is C. Let learning continue. That brings me to the end of this lecture. Thank you for your attention.